Hello, robot learning community. I'm Tianjian from Columbia University, and I'm with my colleague Zhanpeng to present our paper on HWasP policy, which is a mechanical and computational co-optimization method using deep reinforcement learning. First of all, we want to make the point that mechanisms are similar to control policies in a way that both can take some states as inputs, make conversion, and generate outputs. For example, a gear transmission takes in the input angle and torque and converts them into output angle and torque. A spring can take in a deflection and converts it into a force, etc. In traditional RL in robotics, the actions generated by a policy are motor commands, and the robot hardware, which is usually included in the environment, converts motor commands into the effects in the outside world, for example, a change in the object position. In HWasP policy, we move the part of robot hardware we wish to optimize out of the environment, simulated as auto-differentiable physics in the form of a computational graph and connected with the neural network computational policy. Thus, our agent contains a computational component and a hardware component. In this way, gradient can flow over the hardware policy and computational policy via efficient backpropagation. And the hardware parameters and neural network weights and biases can be optimized in the same fashion via gradient descent. We note that the entire training happens in simulation, and after that, we build the physical robot based on the optimized hardware parameters and deploy the computational policy to this robot. Next, I will give the stage to Zhanpeng to talk about our design example to co-optimize the mechanism and control of an underactuated hand.
Thank you, Tianjian. My name is Zhanpeng, and I will be talking about our robotic experiments. In this problem, we aim to optimize part of the design of an underactuated robot hand, more specifically the transmission that converts motive force into joint torques. We simulate the transmission model as a computational graph and optimize the radii of the tandem pulleys at each joint, as well as the stiffnesses and preloads of the joint springs that provides extension torques. In addition to the mechanical policy, which comprises the transmission, we also optimize a computational policy, which controls palm position at the motor set point. We use grasping tasks to test HWasP policy and ask an agent to grasp an object and reach the desired position. Our experimental results show that our algorithm produces both hardware parameters and a computational policy that allows stable grasping for objects of different shapes. For example, spheres, cubes, and cylinders. We also compare our method with two baselines. The first baseline uses CMAES or ARS, which are two evolutionary algorithms, as outer loop to optimize hardware parameters and RL as inner loop to learn a computational policy. The second one is using CMAES or ARS to optimize a joint policy to solve the task. Our results indicate that HWasP policy outperforms both baselines we analyze here. HWasP policy also allows us to learn effective hardware parameters to build a real robotic hand. We successfully built the first prototype using an optimized transmission model, and the optimized hand is able to execute various stable grasps with real-world objects. We also tested our learned computational policy in real world using a UR5 robot. The computational policy, trained jointly with the hardware parameters, is in charge of positioning the hand and of controlling the hand motor. Here, we show that our policy can grasp similar objects used in the training. We hope this work can open up new opportunities for task-based hardware-software co-design of robots or other intelligent systems for researchers both in RL and in the hardware domain. Thank you very much for watching.